Hi guys, hope you're doing well. Here we have a chemistry paper, September exam, written in 2024, Gauteng province. If you want to download the paper, check the description below. Consider the flow diagram below. So what we have is propene, something is being done and then it's developing or forming compound X. So what is compound X? Well, let's have a look at propene. Propene is a 3-carbon molecule. It's got the ene, so it's got a double bond, so let's put it there. And then obviously we would have hydrogen everywhere else. Let's go draw the hydrogens just to be correct here. Okay. And so all that's actually happening here, if you understand your reactions, you would know that this is an alkene. And we know that alkenes are always keen to do addition reactions. They love having things being added because we can see that there's an open spot over here and an open spot over there, and if we want to add something we can, and then we simply have to get rid of that double bond. And so we add a whole bunch of things to them. We can add hydrogens, we can add halogens, but here we're adding hydrogen. So we're just going to add hydrogen. The platinum just serves as a catalyst, for example. And so here we've got hydrogen. And so this is the molecule that we form. And so that is just going to be propane. Which of the following compounds has the highest vapor pressure? Right. Now, when you look at highest vapor pressure, I want you to immediately think of that as being the same as the lowest boiling point. If something has a high vapor pressure, it has to have a low boiling point, and the other way around is true as well. Let me quickly explain. Let's say we have a container, and that container is filled with liquid, okay? So, and then let's say we've got 3 molecules inside there, and that is in the liquid phase. Now we know that whether you have liquid, solid, or gas, there's always going to be intermolecular forces in between the molecules. Molecular force. Now, in order to convert liquid into gas, let's do it in a different color. Into gas molecules are more spread out. In order to go from this phase over here to this phase over here, you need energy. You need energy to be able to overcome these intermolecular forces and then allow them to get out of this liquid phase and enter the gas phase. So to go from liquid to gas, energy is needed. Now that energy is provided in the form of heat or temperature. Temperature is like your heat energy. So in the room that you are in right now, there is energy, there's a temperature that you can feel that's maybe 18 degrees Celsius. So if something has a very high boiling point, it means that the temperature needed to cause it to go from a liquid to a gas is very high. And if something has a very low boiling point, it means that it doesn't need that much energy in order to convert it from a liquid to a gas. So if something has a very low boiling point, it means that it is very easy to be able to convert it from a liquid to a gas. So if something is very easy to convert from a liquid to a gas and doesn't need that high of a temperature, then what does that tell us about the intermolecular forces between the molecules for that substance? Does it mean that those intermolecular forces are extremely strong or extremely weak? It would be extremely weak, because if these are extremely weak, then it's very easy to be able to separate them and cause them to go into a gas. So a low boiling point means that the intermolecular forces are weak. Okay, Kevin, but how does that come back to high vapor pressure? Well, think about this. If something has a very weak intermolecular force, it means that it's going to have a very low boiling point, and it means that all of these molecules are easily going to go into the gas phase. So maybe if we have like, I don't know, 1, 2, 3, 4, 5, 6 of these molecules, most of them are going to go into the gas phase very easy. And so we could actually just convert all 6 of them into the gas phase. So now if you look in the gas phase, we've got we've got a lot of gas molecules. Now, what do these gas molecules do? They create vapor, because they gas, pressure. They create some type of pressure. So if something has let's go over this one more time. If something has weak intermolecular forces, it means that it's very easy to convert them into a gas, meaning that the boiling point is very low. So because we are so easily able to convert them into gas, there's going to be a lot of gas molecules and a very little amount of liquid molecules. And so because of there being a large amount of gas, there's going to be a very high vapor pressure, because vapor is from gas. And so what we need to go and do is look through this list and find the one that has the lowest or the weakest intermolecular forces. Now, what we need to identify is that all of these are alkanes. They're just simple alkanes. This is a 2-carbon, 3-carbon, 4-carbon, 5-carbon. So I don't know if you've gone over this before, but we know that alkanes, the only intermolecular force between them is London forces. You know, we get London, dipole, hydrogen. Well, with alkanes, the only forces they have is London forces. So then how do we tell the difference between the overall strength for this one or for all of these? Well, it's got to do with the length. We know that ethane is a 2-carbon chain, or 2-carbon molecule. Propane is 3, butane is 4, and pentane is 5. So what we've learned is that it's very simple, guys, if you think about it like this. I want you to imagine, I'm going to try to simplify this. So let's say you have ethane. So here we've got one ethane molecule, and now here we've got another ethane molecule. And now I'm going to simplify things. Let's just imagine that there's one intermolecular force over there between those 2 carbons, and then there's one intermolecular force over there between those 2 carbons. So if you wanted to be able to take this and to be able to separate these 2 molecules from each other, then how many London forces would you have to overcome? Well, you would have to overcome 2, okay? Now, don't say that in an exam. You don't want to say in this one there's 2. I'm just showing you the idea behind this. Now, if you had to look at propane, if you had to go draw another propane, you would realize, oh, you have to now separate 3 London forces. And then for butane, you'd have to separate 4, and for pentane, 5. As I said, don't say that in an exam, but what I'm trying to show you is that the longer the chain, it's almost like there's more surface area available for London forces to be able to act. So the longer you make the chain, it's going to require more energy, or it's going to be more difficult to separate them. So which of these molecules are going to be the easiest to separate? Would it be easiest to separate these ethanes from one another, or is it easier to separate pentanes from one another? Imagine you drew another pentane over here. Remember, you always have to think about 2 molecules. So if you had to, so what you should identify is that it's going to be more difficult. It's going to be more difficult to separate pentane, and it's going to be more easy to separate ethane molecules. And as you go down, it's going to get more difficult. So the easiest ones to separate are going to be ethane. So what we'll say then is that the answer is ethane, because that would have the weakest intermolecular forces, which means it's the lowest boiling point, which implies that's the highest vapor pressure. During the dehydration of butan-2-ol, which is an alcohol, okay, we know that alcohols can undergo elimination, and one of the types is dehydration, which is when you take this alcohol and you remove water. That is what dehydration means. You're removing water. Okay, let's actually make a little note here for ourselves. It's the removal of water. So you can do that to this molecule, and then a major compound that is formed is Y. Which of the following is the correct condensed structural formula? Right, now, I've been teaching for way longer than you have been in high school, for example, and I still don't like to use the condensed. I always expand it. So what I'm trying to say is, don't try to figure it out from these things. Rather draw it out so you can clearly see. So we have a CH3, then we have a CH2, which looks like that. Then we have a CH. Let's also put our hydrogens for these ones. And connected to that is an OH. Okay, and then we have a CH3. Ooh, there's something good coming up here. Have you ever heard of Zaitsev? Stick around. Okay, so what we know is that Kevin just said, when you take an alcohol and you dehydrate it, you remove water. So how are we going to remove water here? Well, we're definitely going to eliminate that part. But now here's the catch. We've gotten rid of that, but now you're going to look at the carbon on the left and the carbon on the right. One of those is going to have to give away a hydrogen so that we can make water, because this is an OH, so we still need a hydrogen. But the question is now, which one? You can't just pick and choose. There's actually a strategy, and that is called Zaitsev. Maybe you've heard of Markovnikov, but Markovnikov only works when we are doing addition reactions, whereas Zaitsev works when we are doing elimination. So the way it works, or the way I've always explained this, is the richer get richer and the poorer get poorer. But now remember, this first part, that's when we are doing addition, and that is when we would use Markovnikov, whatever. I always get the spelling wrong. And then this one is whenever we are doing elimination, and that is when we would use Zaitsev. So we are, in this question, we are busy with elimination, so we're not going to worry about that. So what do I talk about when I say the poorer get poorer? Well, I'm talking about hydrogen. This entire riddle is based on hydrogen. So it says that the poorer is going to get even poorer. So you look at this carbon and you look at this carbon and you see how many hydrogens they have. This one has 2. Can you see that? Okay. And this one has 1, 2, 3. So who is the poorest? Who has the least? Well, it's this one. And so what does the riddle say? The poorest one gets even poorer. So we're going to remove the hydrogen from this carbon over here. It doesn't matter whether you take the bottom one or the top one. That's up to you. So I'm just going to eliminate that one over there. And so let's just take that out completely. Now what we'll notice is that we now only have around this carbon there's only 3 bonds, and around this carbon there's only 3 bonds. So to fix that, we put a double bond. Okay, so now we can go do our condensed. So we start from left to right. So we have a CH3 unit. So let's put that there. Then we have a CH unit. And then we have another CH unit. And then we have a CH3. Okay, so the answer would have to then be this one, CH3, CH, CH, CH3. The complete combustion of 1 mole of butane needs at least how many moles of oxygen? Okay, very easy. We've learnt about in organic chemistry that we get combustion, and combustion is when you take let's just quickly remind ourselves, combustion is when you take some type of substance or material, you react it with oxygen, and the product will always be CO2 and water. So what we'll do is we'll take butane, which is a 4-carbon alkane. So if you had to go put all the hydrogens, or maybe you remember that alkanes, they have the general formula CN H2N plus 2. So if it has 4 carbons, then it would have to have 10 hydrogens. Okay, so like that. Then you say plus oxygen. Then you say goes to CO2 plus water, and then we balance. How I've taught you, always balance the carbon first. So on this side we have 4. That means we're going to put a 4 there. Second step, balance the hydrogen. So here we have 10. That means we'll put a 5 over here, because then we also have 10. Last step, balance the oxygen. So on this side we have 5 plus 8 oxygens, because 4 times 2 is 8, and then 5 times 1 is 5. Okay, so 8 and 5 is 13. So now we need 13 oxygens on this side. The only way to do that is to say 13 over 2, because if you say 13 over 2 multiplied by 2, that is also 13. But now the problem is we're not allowed to keep fractions. So what we then go and do is we multiply everything by 2. So this ends up becoming 2 C4H10 plus 13 O2, and that'll give you 8 CO2 plus 10 H2O. So it says that the complete combustion of 1 mole of butane needs at least... Now, a lot of learners are just going to say that the answer is 13. However, we need to look at the question, the complete combustion of 1 mole. So if we look at the mole ratios here, the mole ratio says that for every 2 moles of butane, we need 13 moles of oxygen. That means for every 1 mole of butane, you would need half of that number, which is 6.5. So for every 1 mole of butane, you're going to need exactly 6.5 moles of oxygen. Now, I don't really like the question. It says the complete combustion of 1 mole of butane needs at least. Well, technically, it needs at least 6.5. So I don't know why that's not an option over here. You don't have to round off moles. So if I designed this question, I would have made this a 4. I would have made this like, I would have made this maybe like a 3. And then I would have kept this maybe as a 7 like it is, or even as like a 6.5, for example. But they're pretty much saying how much how much oxygen would we at least need. Now, you can't choose B as an answer, because 5 is going to be less than that. 5 is less than this number. However, the number 7 would work. If you have 7 moles of oxygen, that would work. But so would 18. That would also work. I mean, if you have 18, it's definitely more than enough. And 13 would also work. It's also more than enough. So I went and looked at the memo. And the memo actually says, if a learner chose A or D or C, then all 3 are taken as correct. The most correct, I would say, is that one. But yeah, bit of a weird question. Just don't choose B, okay? The Maxwell-Boltzmann energy distribution curve shows the number of particles as a function of their kinetic energy at 4 different temperatures. The minimum kinetic energy needed for effective collisions to occur is represented by E. Okay, so we've looked at Maxwell curves before. Now it says, which of these curves represents the reaction with the highest rate? So the highest rate means the fastest one. And we know that the fastest reaction would always be the one that has the highest temperature. Now remember that for the molecules to be able to react, remember there's always 3 things that are needed. They need to have enough energy, they need to be able to collide, and they need the correct orientation. However, did you hear that one I said? I said they need to collide. That's not that important right now. They need the correct orientation. That's not that important right now, but they need enough energy. Now, that minimum energy that is needed for the particles to react is called activation energy, which is this one over here. And so it's only the molecules on the right of that are actually able to react, because this is the energy on the x-axis, sorry. And so everything here, their energy is too low, so they can't react. And then everything on the right, they can react. So we're looking for the graph that gives us the maximum or the biggest area on this side. So if you look at graph A barely gets there. If you look at graph B, it only gives us this little portion over here. If you look at graph C, it's a bit better. But then if you look at graph D, look at how nice and look at how big the area is on this side. It's all of that. So the one that's going to have the more reactions taking place is always going to be the one that's at the highest temperature. And so it's definitely going to be curve D. The graph below shows the changes in X, Y, and Z over time during a reaction. Okay, so here's X, Y, and Z. So they are obviously involved in a chemical reaction, and you can see that they are increasing and decreasing over time. We can see that in the beginning, there is no Z. See that the Z is 0 at the beginning. So the Z is definitely a product, as we can see, and then the X and Y, they both start over here, so they must definitely be reactants, and that's why we can see them on that side of the reaction. Now it says, which of the following balanced chemical equations is correct for this reaction? Okay, so what you need to understand, now if you look at X, it started at 2.5 and it ended at 2. Okay, so X was 2.5 minus 2, so how much did it go down by? Well, how much did it change by? It changed by 0.5. If you look at Y, it started at 2.5 moles and it ended at 1 mole. So how much did it change by? It changed by 1.5. Okay, and then if you look at Z, how much did it change by? It went from 0 to 0.5. So let's just say 0.5 minus 0. So it changed by 0.5. So if you now look at these, let's simplify those into a simplified ratio. So I know that if I divide all of these by the smallest number, if I divide all of them by 0.5, it's almost like doing empirical formula. We're getting 1, 3, and 1. Those are going to be the mole ratios that you need in the chemical reaction. Because in a chemical reaction, they are telling you for every 1 mole of this, you need 3 moles of that, and blah, 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 blah. And for every 4 moles of that, you need 2 moles of that to make 1. Those ratios are telling us how the reaction changed. So what we can see is that X is a 1, Y is a 3, and Z is a 1. So the answer must be A. It's got absolutely nothing to do with these numbers, the 2.5 and the 2. It's instead got to do with the change. Remember, when a reaction is happening, that is telling us what is changing. It's not telling us that how much we're starting with or how much we're ending with. It's telling us that for every 1 mole of X that reacts, 3 moles of Y reacts to produce 1 mole of Z. So whenever you are looking at a chemical reaction, these numbers are telling you the ratio of how the reaction is actually happening. It's got nothing to do with the starting and the ending amounts. HPO4 2- is an ampholyte. What is an ampholyte? An ampholyte, I'm going to call my child that one day, because then I can literally say that he's a lighty. Okay, that was terrible. What was I saying? Oh yes, an ampholyte is a substance that can behave as an acid and a base. Okay, so what do acids do again? Acids, they give away hydrogens. And then what do bases do? They accept hydrogens. Okay, so if this bad boy over here, let's say HPO4 -2, and technically it's a hydrogen and a hydrogen like that. So if I take this thing here and I take and it gives away a hydrogen, what does it become? Well, it ends up becoming, there's no more hydrogen, so it just becomes PO4. Okay, and then if it was -2 and then it gave away a positive hydrogen, well, then it's going to end up becoming even more negative. So it's going to end up becoming PO4 with a -3. So the answer is definitely not going to be D, because there's none of that, and the answer is definitely not going to be C, but it could be A or B. Okay, so let's now look at the other part. If we take HPO4 and we rather let it behave as a base, then that means we're going to add a hydrogen to it. So it's now going to end up having 2 hydrogens. Okay, and if it was -2, and now you add something positive to it, then it just becomes -1. So, sneaky. So they have that in both. So I thought we would maybe be able to get away without having to know which is the base and which is the acid. But yeah, they're a bit smart for us. So what we need to understand is that in this scenario, what is this acting as? Well, in this scenario, this thing is acting as an acid because it's giving a hydrogen away. It's giving a hydrogen away. So then that means that this thing over here would be your conjugate base. Okay, and so the answer is definitely going to be the one here where this one is a conjugate base, so B. And yes, we could have also spoken about that one. If you want, I'll quickly do that. This one over here, what is it? It is acting as a base because it is receiving a hydrogen. So that means that the thing that it produces must be the conjugate acid. And so that also fits with what we said. If the concentration of a sulfuric acid solution is that, what will the pH and OH concentration be? Very, very easy. We know that pH is equal to negative log of H3O plus. So where does the H3O plus come from? Well, what we need to remember is that sulfuric acid, H2SO4, ionizes with water, produce H3O plus Now make sure that you do balance the equation. So what we can see is that on the left there is 4 hydrogens, but on the right there is only 3. So what you do is you got to remember that this H2SO4 has how many hydrogens? It's got 2 hydrogens, right? It gives one of those hydrogens to water, and then it gives the other hydrogen to a different water molecule. So how many water molecules do you have? You could almost think of it like this. We will clean it up now. And what we then end up with is, I'm going to explain all of this now, and then we're going to simplify. So remember that this H2SO4 has how many hydrogens? 2. It gives one of those hydrogens to this water molecule, and then another H2, this water molecule. And so we end up producing 2 H3O pluses. And so what we can do is just simplify this to 2H2O, and then this will just become 2H3O. Okay, now you would notice that everything is perfectly balanced because now we've got 6 hydrogens on the left and 6 hydrogens on the right. Okay, so the point is, if we know the concentration of the sulfuric acid, then we can go use those ratios to work out the concentration of that. We can see that the mole ratio is 1 to 2, so that means that this one's concentration will be double, so it'll be 2 times 10 to the negative 3. So now we can go work out the pH by saying pH is equal to negative log of H3O plus concentration, which is negative log of 2 times 10 to the negative 3. And if we type that in, that'll be 2.70 if we round off. So it's definitely not going to be C and it's not going to be D. So it's one of these. All right, now to work out the concentration of H3O plus, we can use the Kw formula, which is 10 to the negative 14. And that's equal to H3O plus and OH minus. Now technically this formula is only supposed to be valid at 25 degrees Celsius. But guys, in a situation like this, there's no other option, so just assume that it's 25 degrees, okay? So we're going to then say 10 to the negative 14, and there is another formula you guys can use. I know some learners like to use the H3O plus POH equals 14 formula. That could also work right now, absolutely fine. Okay, and so we can go 10 to the negative 14 equals to H3O's concentration, which we said was 2 times 10 to the negative 3 by OH minus. Now, if you had to work out OH minus concentration, you're going to end up with that over there. And so if we had to go type that all in, we end up with 5 times 10 to the negative 12. So the answer must be B. Which of the following containers can be used to store an iron sulfate solution? Okay, so what we have in this kind of question is we have a solution. So let's just draw ourselves a container. And in that container, we have a solution. And that solution is iron with a 2 sulfate. So that's iron sulfate. So what you must understand is that this solution is actually broken up into ions like that. Now, the important part of this question is not the sulfate. The important part is the ions. I'm going to ignore everything else. Okay? And we're going to imagine that we've got some ions. Now, why did I say that? Because this is the atom iron, or the element iron, and then it's also got a charge, so it's an ion. Okay, so we've got these ions, these Fe2 ions floating around, and we need to decide what container should the material, or what material should the container be made of? For example, if we use aluminium as the container, what we don't want is we don't want the aluminium and the ions to react. We don't want a reaction to happen. Why? Because the whole goal of this thing is to be able to store. Imagine you have a garage one day, okay, and you've got your car there, and then you've got some iron sulfate that you would like to keep in a container so that you can maybe use it in 6 months. Well, when you come back in 6 months, you still want to have iron sulfate. You don't want to have aluminium sulfate. You don't want these to switch places. You don't want a reaction to happen, okay? So the goal is to find a material, let's say a container material, such that no reaction takes place. Okay, so let's go start with aluminium. Let's just try to figure out our way around this question. So aluminium, remember that is not aluminium 3+, so that is aluminium. So I want you to go circle aluminium. Then what else do we have? We have Fe2+. So let's go find Fe2+. There we go. Okay. Now, and by the way, I should have mentioned this. This is table 4b that I'm using. If you are using table 4a, you can still listen to the way that I think about this, because I'm going to make use of the arrows. That's the important part. So listen to this carefully. There's no battery over here, right? There's no power source. So the only way that a reaction will happen is if it happens spontaneously. So the way that a reaction happens spontaneously is if we have the following. On the right-hand side, you need the material to be as high as possible, because look at this arrow, it's going upwards, okay? So there we've got aluminium up there. And then on the left side, we want the material to be as low as possible. If you have a situation where the one on the right-hand side is higher up than the one on the left-hand side, on table 4a, that would be different, as long as you follow the arrows. If you have a situation where the one on the right-hand side, because of the arrow direction, is above the one that's on the left. You see, the one on the left is going down, the one on the right is going up. So if you have a situation where the one on the left is lower than the one on the right, then a reaction will take place. A spontaneous reaction will take place, okay? However, if you had a situation where the one on the left is higher up than the one on the right, then you see the arrows aren't really being followed. You can see that the one on the right is lower than the one on the left. Then a reaction won't happen, okay? But as soon as you have something like this, for example, a reaction will happen. As soon as you have something like this, then a reaction won't happen. As soon as you have something like this, then a reaction will happen. And as soon as you have something like this, then a reaction won't happen, okay? So spontaneously. So aluminium, we're not going to use. Why? Because if you have aluminium, we said that a reaction will happen, and we don't want a reaction to happen here. So remember, the goal is to find a container material such that no reaction takes place. Okay, so let's go try magnesium. So magnesium is over here. So once again, a reaction will happen. And I will explain it in terms of these reducing and increasing abilities once we find the correct one. Nickel, where are you, nickel? Ah, nickel, look at that. So now, all of a sudden, a reaction won't happen. So the answer must be C. For those of you that don't really care why, you can move on. But for those of you that want to know the reasoning behind it, in the test, you can't say it's because of the arrows. I know some of you are like, yeah, but Kevin, it doesn't matter. It's multiple choice. You don't really have to give a reason. Yes, but they do like to ask this in the actual questions as well. So understanding how it works is important. So once again, we are happy with the fact that, well, the answer is nickel because a reaction won't happen. So as I said, for those of you that are happy with that and you want to move on, you can. But for those of you that want to know why, it's the following. So what you do is you start with this nickel over here, okay? And then you're also going to circle this one over here. And then you're just going to say something like this. Has a weaker, and then you look at this, reducing ability than Fe, and therefore will not be able to reduce. Now what we do is we go to this one, Fe2 plus to Fe. Okay, so that's kind of the way you would think about this. So what I did is that's what we originally had. Then what I do is I take the one that I'm looking at nickel and I want to explain why it's not good enough to cause a reaction. So then I compare it with the opposite of this one, so the one that's on the same side of the table. And so I said that nickel has a weaker reducing ability than Fe and therefore will not be able to reduce. And then I come back to this one, Fe2 plus to Fe. And the reason I can say that it's weaker is because if I look on this table, it says that as the arrow goes up, the ability to reduce increases. So because nickel is lower down, we can say that it is weaker. Let me know in the comments if you are coming to this question now because you've tried this yourself and you probably got this answer and you checked on the memo and it's that answer. Don't worry, I did the same. The problem is, guys, what we are doing wrong is we are reading this part of a year and then we're not completing the sentence. When the cell reaches equilibrium. Did you know that all of the calculations that we do when we sometimes say E cell equals to E cathode minus E anode, when we are doing those calculations, that is when the system has just been set up and it's beginning to react, but it hasn't yet reached equilibrium. So if you went and calculated 0.56, that is, you did the right thing under normal situations, but what happens is that it starts at 0.56 when you first set this up. But if you then allow the system to react for a couple of hours or a couple of days, what eventually happens is that the voltage slowly but surely drops due to the whole your equilibrium slowly but surely starting to be established. The one cell ends up becoming positive, the one cell ends up becoming negative, and eventually the whole system just comes to a complete equilibrium where we then reach 0 volts. And so that was the key word, when it reaches equilibrium. Don't worry, that got me too. I will be splitting the questions up onto individual slides, but here are all the questions we're going to do. First question, is compound A saturated or unsaturated? Give a reason. So let's quickly go check that out. Okay, I can see that it's an alkane, but if you couldn't, it's got a CH3, so and then a CH2, and then another CH2, and then another CH3. So what we can see is that it only has single bonds. And so when it's a alkane, so the only time we ever look at saturated or unsaturated is when we are looking at hydrocarbons. And hydrocarbons are molecules that only have hydrogen and carbon. So if they are only single bonds, then it's saturated. And if there's a double or a triple bond, then we would say unsaturated. So this one has only single bonds, so we will definitely say that it is saturated. And let's just say only single bond. This one says write down the letter that represents the following. This one, a ketone. So we know that a ketone has a carbon with a double bond oxygen, and that carbon is somewhere in between two other carbons. So the answer would be E. You can see over here we've got a carbon there with a double bond oxygen, and that carbon is in between two other carbons. So the answer there would be E. Okay, 2.2.2. A halo alkane. So a halo alkane, let's have a look. So that would be D. We can see that it's got the halogens over there, and so that is a halo alkane. So we'll just say D. And now it says the two functional isomers. So in grade 12 organic chemistry, there are only two pairs of functional isomers. I'll also give you an example of each one, and I'll also explain what a functional isomer exactly is. So the two pairs you need to know are esters. They are functional isomers with carboxylic acids. And then the other pair is ketones and aldehydes. But let me give you an example. Let's say we have a 3-carbon ester. So something like that. And then obviously we've got hydrogen everywhere. And then let's say this one is the double bond. Okay, so that's an ester. Now, if I do a carboxylic acid with 3 carbons, then we'd get something like that over there. And then obviously all of these are hydrogens. Okay, what I want you to do, go count the number of carbon, hydrogen, and oxygen. So carbons, there's 3. Hydrogen, there is 6. And oxygen, there's 2. Then for this one, have a look, 3, 6, and 2. So that is what isomers are. Isomers have the same molecular formula. However, something's different. In this case, it's the functional group that's different. Here we have the ester functional group, and here we have a carboxylic acid functional group. Okay, so that's why they are called functional isomers. Now, the next example is ketones and aldehydes. So let's do a 3-carbon ketone. So that would be like that. Remember, ketone always has the carbon with the double bond oxygen, it always has to be in between two other carbons. Okay? It doesn't have to be directly in the middle of the entire molecule, like we saw over here. It just has to be in between two carbons. Then with aldehydes, aldehydes have the double bond oxygen always on the side of the molecule. Aldehyde, always on the side. Aldehyde, always on the side. I've said it before, hey guys? And so let's go quickly fill this all in. All right. If you now look at the number of carbons, you've got 3. Hydrogens, you've got 3, 6. And then oxygen, you've got 1. If you do the same for this one, 3 carbons, 6 hydrogens, 1 oxygen. So once again, we've got the same molecular formula, but something's different. Well, in this one, we have a ketone functional group. In this one, we have a aldehyde functional group. Okay, so the goal is to look at this table and to either find a carboxylic acid and an ester, or a ketone and an aldehyde. So we know that we already have a ketone down here. So let's start there. We have a 4-carbon ketone, and up here we actually have a 4-carbon aldehyde. We know that the but means 4, and when it ends with the word butan and then al, that is aldehyde. See the al? That's aldehyde. And so that would be the answer, E and B. This question over here says, consider compound C. Okay, there it is. Is compound C primary, secondary, or tertiary? Okay, so that one is going to be primary, but let me explain. For those of you that just want to skip ahead now, if you understand why it's primary, that's great. But for those of you that don't, let me quickly show you. So what you do, right, I'll give you an example of a primary. What you do is you have a carbon connected to an OH. That is what an alcohol is. Then connected to that carbon, we want it to be touching one other carbon. So let's just put our hydrogens, put another carbon. Okay, I'm not going to draw all the hydrogens, but have a look at this. You've got a carbon, right, that is touching the OH. Now I want you to look at that carbon, and how many other carbons is that one directly attached to? Well, it's only attached to 1. So we call that a primary. Now, if we're looking at a secondary, you would have something like this. You would have a carbon attached to an OH, of course, and then you would have something like this, and like that, and like that. So now, for example, you've got carbon attached to an OH. I then want you to look at that carbon. How many carbons is that one touching? Well, that one is touching 1, 2, so we call that a secondary. And then lastly, tertiary would be a situation like this. And then obviously the rest of these things are just going to be hydrogens. So what we see is that the carbon that is attached to the OH is this one here. Now how many carbons is that one touching? 1, 2, 3. Okay, so now we come back to this one. Have a look at the carbon that has the OH. There it is. How many carbons is that one touching? Only 1. Hence, it's a primary. And the reason for that is that the carbon bonded to the hydroxyl is the OH, is bonded to 1 carbon atom. Okay, this one over here says, write down the structural formula and IUPAC name of a chain isomer of compound C. So remember once again, what are isomers? Well, molecules with the same molecular formula, but something is different. Something in the structure. If function group is different, then we call it a functional isomer. If length of carbon chain is different, then we call it a chain isomer. And then if the function group, I'm not going to repeat this part, don't worry. If the function group is the same, but in a different position, then we call it a position isomer or a positional isomer. Okay, so the question says, write down the structural formula and the IUPAC name of a chain isomer of compound C. So they should have said here, not on table, or not necessarily from the table. So here we have a, it's an alcohol, and we can see that it's got 3 carbons in the main chain. So all we'll do is we'll just take, instead of letting this one be a branch, we'll just let it be a part of the main chain. So instead of it being a 3 carbon, it would now be a 4 carbon. Okay, and everything else is the same. So this is the structural formula. Okay, that is your structural formula that they want. The name, because they also want the IUPAC name, that's just going to be, it's an alcohol, so you just say butan, and then the OH is on carbon number 1. So butan 1-ol. Okay, we still have more questions. Write down the IUPAC name for compound D. Okay, so compound D. Right, so here's compound D over here. So step 1, find the longest continuous chain. What is the longest continuous chain? It's the longest chain you can make without lifting your pen off the paper. So I'm going to try this way first. So that's 1, 2, 3, 4, 5, 6, 7. Then I want to just try this way. Okay, that's only 6. Okay, so the longest is going to be 7. 1, 2, 3, 4, 5, 6, 7. Okay, so immediately I know that that means hept. Okay, then I can see that this is just a basic haloalkane, so I know that it's going to end like that. And now I've just got to think about all the branches. So the branches are going to be everything that is sticking off the side. So it's going to be this that is sticking off the side, and then these two. Now we got to, all right guys, so as you saw, my laptop's about to die. If I give banking details, could someone maybe dollar me a 50 rand so I can put some electricity in? Things are running a bit low this month. Yeah, I don't know how I'm going to do this, because you're not going to see this video until it's done. And so, yeah, I think things are going to switch off quite soon. It's going to be okay. It's going to be okay. Guys, I'm joking. Let me plug this thing in. Yo, when I said the word dollar now, I remember I live in the Western Cape now, like near Cape Town nowadays, but I come from a town near Durban called Ladysmith, and I was born there, lived there until about the age of grade 8, I would imagine, yeah. And in primary school, I had a lot of Muslim friends and Indian friends in Ladysmith, and I can't remember the name of the area now. I know there's an area called Settlers Park, and then just next to that, there's like quite a big Muslim area. Well, I used to have a lot of friends there, and I used to go into that area a lot. And I used to go hang out with my friends, and we used to play Xbox. We always used to play FIFA, if you know, you know. And we always used to go to indoor football. There was like a indoor sports center in Ladysmith. It's where they used to have like the fair, like the fun fair and all of that, like where all the roller coasters and all of that. Anyways. So I always used to go visit these guys, and I'm just like the only white guy, and then all my friends are like Muslim and Indian, and we go into these like these areas, and I remember we would like walk on these streets, and on every like corner there's like some bra park there in like his little camper van selling hot dogs, and I promise you there is nothing better than those hot dogs. But yeah, I just remember being with my Muslim friends, and they're always like, are we given dollar me a 10 rand? Okay, no, it wasn't that accent. That's more of a colored accent, but it was more of like a yeah, I can't remember it exactly, but yeah, if you know, you know. Just imagine Kev there, only white guy in the group, but he loved his soccer. And it was so funny, I used to like literally be sitting in these guys' houses, and it would be like 6 of us on a couch, and we all just sharing the Xbox controller, and we've got like our hot dogs there, and some of them had Gatsby's and stuff, and then the moms would come home, like the aunties and stuff, and they would be like, hello Kevin, you Kevin. Oh, it was amazing. I loved it. Those were the days. Anyways, where were we? Oh yes, we're busy naming. And so how did I get onto the word dollar? Oh, my laptop was about to die, and I needed someone to dollar me a 50 rand. Okay, anyways, just carry on. Yes, so now we need to look at the branches, and we need to make the branch numbers as small as possible. So, if we chose this as our position 1, then the branches would be on carbon number 3, carbon 5, and carbon 6. So that's 3, 5, 6. Now, if instead we name it from the left, well, then you're going to get branches on carbon number 2, 3, and 4 and 5. Okay, so 2, 3, and 5. So overall, we can see that these numbers are lower than these numbers. So we're going to name it from the left. And so we've got bromo branches and methyl branches. It must always go alphabetically. So B comes before M. Okay, so on carbon 2 and 3, we've got bromo. So we're going to say dibromo. Okay, let's move this up. And then you always put a hyphen. And then on carbon 5, we have a methyl. And there we go. Okay, this question says, name the functional group of compound B. Now, they didn't say draw it. They said name it. However, I'm going to obviously draw it just so we can have a deeper look into this. So we know that that was the aldehyde. So we know that aldehydes always have a double bond oxygen on the side. Okay, so this is the functional group. It's this part here. Now, what is the name of that? Well, you know how we get different names, like the OH part in an alcohol is hydroxyl, the C double bond oxygen in a ketone is called a carbonyl, but when you've got the C double bond oxygen with the hydrogen, well, then it's a weird name. It's actually a formal, like that. This question says, a sample of compound F, which is this one here, contains 40% carbon, 53% da-da-da. If the molar mass is 60, calculate the molecular formula. Jeepers. This is like empirical slash molecular formula stuff. Okay, so we have 40% carbon. If you know how to do empirical, like this is just easy marks actually. 53.3% oxygen, so specific. And then X% hydrogen. Okay. So what we do is we pretend that these are masses. Now we know that percentage always adds up to 100. So what we do is we pretend, okay, let's pretend we have 100 grams. So that means we've got 40 grams of carbon, 53.3 grams of oxygen. And then if you say X, well, we know that these percentages must add up to 100. So X would be 100 minus 53.3 minus 40, and that's going to end up giving us 6.7. Okay, so 6.7 grams of hydrogen. The next step is to convert all of these into moles. Okay, so to do that, we're going to obviously just use the good old N equals to M over capital M. Now, obviously, you can go get these on the formula sheet, but I'll just, the molar mass of carbon is 12, the molar mass of oxygen is 16, and the molar mass of hydrogen is 1. So we're going to say 40 divided by 12, and that'll be, whenever I say that'll be, I've probably said this before, I think but I always think about the movie Shrek. I don't know if you ever watched it, but by the way, I was alive when Shrek came out. It was like 2000 and, jeepers, when was that? 2000 and, I can't remember. It's probably like 2001, somewhere around there. But I was there and I went and watched it at the cinema when it came out. And there's a part, I can't remember if it's Shrek 1, but he always says, that'll do, donkey. That'll do. So whenever I say that'll be, that's what my mind does. Yeah, try living in this mind. Okay, so that's going to be 3,33 moles. And then this one's going to be 53,3 over 16. And that'll be, that'll do, donkey. That'll do. Also 3,33. Things are looking sweet, my bro. And then this one will be 6.7 divided by 1, which is 6.7. So clearly, we can see that the ratio, you can see these are going to be 1 to 1. And then this number here is pretty much exactly double that. Okay, so we're going to just simplify the ratios now to 1. Well, the way we do it is we divide all of these by the smallest number. So we divide all of these by the smallest number. And so that ended up becoming 1. 1, and this one will be like a little bit more than 2. 2.01. You can round that to 2. That's fine. Okay, so there we have the ratios now. By the way, if you're confused with this is just empirical formula. So that's why I'm not going super slow. I'm going quite quick because I assume you've gone over it. If you haven't, just look for videos on empirical formula. Righto. So if the molar mass calculate... Okay, so the empirical formulas... So we've got C, H, and O. So C, we got a 1. H, we got a 2, and oxygen, we got a 1. Now, don't write the ones there, so it's just going to look like that. That is called the empirical formula. It's the simplified ratios. Okay, now, they want the molecular, but what we have is the empirical. So all that you go do now is you go work out the molar mass of this. So that means you go look on your periodic table, and you'll see that there's 1 carbon, 2 hydrogens, that's going to be 2, plus 16 for oxygen. And that's going to end up giving you a total mass of 30 grams per mole. However, they tell us that the molar mass of the molecular formula, or the real molar mass of this molecule, is 60. So the real mass is double the empirical. So how do we get this to become a 60? You're just going to double all of these. So it's going to end up becoming C2H4O2. That is the molecular formula. So the empirical is the simplified one. The molecular is the real one, what it actually is in real life. This one says, write down the IUPAC name of the 2 organic compounds that will have this molecular formula. Okay, so it's not from the table. C2H4O2. Okay, so that could be something like, okay, it's going to have 2 oxygens. Okay, so the only ones that have 2 oxygens are our carboxylics and our esters. So that would be, this would be an ester. Esters have this COO like that. Okay? And then your carboxylic acid would be, ester's the only one that has an oxygen in the actual chain. All right. So the name of this, well, we know that to name esters, it's always the alcohol part first, which is this part, and then it's the carboxylic acid part. Because remember, an ester is an alcohol plus a carboxylic acid. So it's going to be a 1 carbon alcohol, which is methyl, and then a 1 carbon, this part, so you're going to say methanoate. Okay? And then for this one, it's just going to be a 2 carbon carboxylic acid, which is just going to be ethanoic acid. The table below shows the boiling points of 4 organic compounds represented by letters A to D of comparable molecular mass. Okay, so what we have here is we have a haloalkane, an alkane, methyl propanoate, that is an ester, and then we've got an alcohol. Okay, and then we can see the different boiling points. All right, so it says 3.1, compounds A and B are structural isomers. Okay, so they like to talk about isomers in these exams. So remember, isomers have the same molecular formula, but the structure is different. Now you either get position isomers, chain, or functional. Okay, so they said compounds A and B are structural isomers. Define the term structural isomers. Okay, so here's the basics of it, but now I'll go get you the proper definition. Okay, so here it is. It's organic molecules with the same molecular formula, but different structural formula. It says here that the boiling point of compound B is higher than the boiling point of compound A. Explain. Okay, so here we've got A and B. Okay, so if we go draw this one out, it's just a butane molecule. So let's just say here 2,3 dimethyl butane. It's a 4 carbon, and on carbon 2 and 3, it's got methyl branches. Okay, or you could even put the one going down, one going up, just for a bit of better space. Okay, and then obviously the hydrogens are everywhere. I'm not going to go fill those all in, but that's sort of what it would look like. And then hexane is just a 6-carbon straight chained alkane. Okay, now they want us to talk about boiling point. Now remember, with boiling point, you always have to draw at least 2 of the molecules in order for you to make a good comparison. So that is what 2 hexane molecules would look like. Now obviously there's hydrogens everywhere, so let's actually just do that. So I'm not going to go fill the hydrogens in, but you know that they are attached to all of those lines. And then here would be another hexane molecule with obviously all of its hydrogens. Okay, and then for this molecule, we've obviously got 2 of those. So let me get some space quickly. Okay, so here we've got 2 of these molecules, and then here we've got 2 of the hexanes. So this one is these ones over here, and then this one is these over here. Okay, now immediately, without even looking, I would know that hexane is going to have the higher boiling point. And the reason is this, guys. We know that in this molecule here, there's only London forces, and in this molecule here, there's also only London forces. So both molecules only have London forces. However, London forces are not all equally strong. It depends on a couple things, such as the length of the chain, or whether there are any branches or anything like that. So the way I think about this is, you see with these 2 molecules over here, because they don't have any branches, they are able to get quite close to each other. They can get nice and close to each other. And so because they can get nice and close to each other, they can hold on to each other more strongly than these molecules can. These molecules can't get that close to each other because these branches get in the way. So as soon as they get close to each other, the branches kind of get in the way, and they can't really get close. But the technical reason as to why these have weaker intermolecular or weaker London forces, yes, it's because of the branches, but what the branches do is they cause the surface area that is available to become less. So the more branches you have, the less surface area you have available for London forces to act. So because these London forces are not going to be as strong, it would be much easier to separate these from each other. So that is why their boiling point is lower, because you don't need as much energy to separate them. Whereas these, they can get nice and close, and there's a large surface area. So the surface area is the main thing we're talking about here. Because they have more surface area, a larger surface area, the London forces are stronger. And so you've got a larger boiling point. So now for 3 marks, we need to explain. Okay, so I would say both A and B only contain London intermolecular forces. Okay. However, hexane, or you can actually just say B, has a larger surface area. You can say that the London forces, or let's just say the intermolecular forces in B, are therefore stronger. And then your last point, you could say more energy is needed to overcome. Don't use the word break, use the word overcome. More energy is needed to overcome the intermolecular forces in B. This question says, define the term vapor pressure. So vapor pressure, all you need to understand is that if you have a liquid, okay, you've got a liquid, when it starts to boil or evaporate, it's going to go into the gas phase. And as soon as it's in the gas phase, we call it a vapor, and it will then begin to exert a pressure. So that's so the definition is the pressure exerted by a vapor which is in equilibrium with its liquid, and then importantly, in a closed system. Okay, so the system must be closed. And so, yeah, that's the definition. Which one of the following compounds, B or C, will have a higher vapor pressure? Right, now, we've spoken about this before, but high vapor pressure just means low boiling point. So substances that have low boiling points have higher vapor pressures, and substances with higher boiling points have lower vapor pressures. So they're just looking for B and C. So I look at the boiling point, and I look at the one that has the lowest boiling point. So the answer would have to be B. And then we can just say it has a lower boiling point than C. Okay. This one says, consider compounds C and D. Okay. Will the boiling point of compound D be X or Y? So they're pretty much saying, would it be higher or lower than this one? Because if it's X, then it's 75.5, which is lower. And if it's Y, then it's 135.5, which is higher. That's essentially what they're asking. So what we have here is a 4-carbon. So this is a 4-carbon ester. And this is a 5-carbon alcohol. Now, if you look at an ester, any ester, it's got this kind of functional group. And there's no OHs. So esters don't have hydrogen bonds, whereas alcohols, they do have hydrogen bonds. And we know that out of these intermolecular forces that we consider in organic chemistry, the hydrogen bonds are the strongest. So we would definitely expect that this molecule is going to have a higher boiling point. So it's definitely not going to be X, it's going to be Y. And there's even another reason. This is a 4-carbon molecule. This is a 5-carbon molecule. So we could even argue that the length of the chain is longer, so the London forces are stronger because of larger surface area. But all we actually need to go and do is say the following. We just go and name we first mention the intermolecular. So normally it's a 4-mark question, but now it's just a 3-mark question. So your first step can just be to say what the dominant intermolecular force is for each molecule. So we could say that compound C has dipole-dipole forces between its molecules, whereas D has hydrogen bonding. Yes, they also have London forces, and alcohols also have dipole-dipole, but we're just going to mention the dominant one. Okay, the dominant one. So D has hydrogen bonding. In your next step, talk about dipole-dipole versus hydrogen bonding. So we can say hydrogen bonding is stronger than dipole-dipole forces. Then we can summarize. Therefore, more energy needed to overcome the intermolecular forces in D. I will be splitting these questions up, but here are all the questions we're going to do. So let's begin. First question, write down the type of reaction that occurs at A. So at A, let's see what we have here. So I would always go draw this out for myself. So we've got CH3, then we've got a CH, then we've got a CH2. Okay, so immediately I can see that this carbon and this carbon only has 3 bonds. So I need to make a double bond in order to make this carbon have 4 and this carbon have 4. Okay, so what we have is an alkene. Now we know that alkenes are keen to do addition. They love doing addition. Why? Because what we can notice is that there's an empty space over here and an empty space over here. And if we want to fill up those empty spaces, all that we need to do is break one of these. Okay, so this is definitely going to be an addition reaction because that is what alkenes love to do. So we can just say addition. Now specifically, if you wanted to, we are adding HBr. So you could say hydrohalogenation if you wanted to, if you're cool like that. Write down the type of reaction that occurs at C. Well, C is the exact opposite. So that would just be hydrohalogenation, or you could say elimination. So let's just also fill in here earlier, hydrohalogenation. Now you can just do the opposite, elimination or dehydrohalogenation. This one says write down the name or the formula of the catalyst at D. So at D, we're going from an alkene, like we said, and then this is an alkane. So we know that that uses either platinum, palladium, or nickel as a catalyst. So they said write down the name or formula, so we can just keep it as platinum. But then you could also have used, you only have to give one, okay? But I'm going to go give you your different options. Reaction B is a substitution reaction, okay? So we must know that this is a haloalkane, because here we had an alkene, and then we added this to it. So then you're going to have a haloalkane. Now they say that reaction B is a substitution reaction that takes place in the presence of water. So if we remember our diagram where we show all our different reactions, we should know that the haloalkanes, they can either go back to alkenes, which is what we saw over here, or we can become an alcohol. And to do this pathway, we always use, this is the one where we use concentrated base, concentrated strong base, like NaOH or KOH. This one over here, we use dilute strong base, which is also NaOH, KOH. But we could also use water for this one. We can also use water. Okay. So it says write down the type of substitution. Well, all of these are called hydrolysis. And then it says name 2 other reaction conditions for this reaction. Now, I don't really agree with what they've said on the memo for this one. Let me explain. So when you have a haloalkane, we know we can convert it to an alcohol. Now, there's 2 main ways that they do this. One of them is we use a dilute strong base. And yes, the dilute is because there's water present. I get that. Dilute strong base, such as NaOH and KOH. But then the other method that they use in industry is they don't use a base. Instead, they just use water itself. And then they would have like excess water. So they would say something like excess water. Okay, this one's usually a little bit slower. But now, so there is water in this one, of course. That's the only reason something can become dilute. However, they said here is a substitution reaction that takes place in the presence of water. So it's a bit tricky, like, do they want us to focus in on this one? Do they want us to focus in on that one? But on the memo, they said that you need a dilute strong base and you need to use some heat. Now, you see, it's a little bit open-ended, right? Did they mean like excess water or whatever? So usually I haven't seen this before where there's a bit of a gray area here. But I honestly, when I said water, I honestly thought of, okay, it's this one. So I'll give you the answer for both, and then in an exam, hopefully it's more clear for you, okay? So if it was the one where we use the strong base, then that's the condition. You need a dilute strong base, and then you also want to use heat. Okay, so those are your 2 reaction conditions. If it was number 2, well, the one condition is you need excess water, so like a lot of extra water, and then you're also going to use heat. Okay, so I'll leave it there for you guys, but they focused in on this one on the memo. Now, that one's done, that one's done. Okay, now it says, what is the IUPAC name of the major product Y? Okay, so that's going to be an easy one. Okay, but to do that, we're going to have to get a better idea of what this one looks like. So let's quickly check. So here we had, remember we had an alkene, which looked something like that, okay? Then, and it doesn't matter whether you put this line down here or whether, yeah, whatever. You could even have this one over here and this one open. It doesn't really matter, but that's what we had. Then what we do is we add HBr to that. So you need to try and understand, where does the Br go for this reaction? Where does the Br go and where does the H go? So this is where we use Markovnikov's rule, which tells us that the rich get richer and the poor get poorer. Remember that one? Rich get richer and then the poor get poorer. So this part here is what we are focusing in on, because this is where we look at addition. whereas this one is only if we were doing elimination. And what are we talking about? We're talking about hydrogen. So if you look at these two carbons, this one currently has 1 hydrogen, and this carbon currently has 2. So it tells us that the rich get even richer. So this is the richest one. So that means the hydrogen is going to go there, and then the Br would obviously go to the other one. Okay. And so we nearly had a DJ colored there, but it was another one, not the other one. Okay, Kev, move on. No one cares. Okay, so thanks, guys. So right, we've got that now. So now we are here. Now, if we had to now go convert to an alcohol, all that would happen was that this would be replaced with an OH. And there we now have our alcohol. So they want to know, what is the name of that thing? Well, the name of that thing would be, it's 3 carbons, so it's propan. And then on carbon 2, there's an alcohol, so it's propan 2-ol. This question here says, use the structural formula. Oh, and by the way, guys, remember we still have more questions coming up. Use the structural formula to write a balance equation for reaction B, okay, which is the haloalkane going to the alcohol, showing the formation of the alcohol. Okay, so we already looked at, so let's just quickly go re-look at that. Remember we said compound B looks like this. It's got the Br in the middle there, and the rest is all hydrogen. And then we react that with, for example, water, okay? And the product you would then get. So what happens is that you can think of water as this. And so we know that these two are going to switch place. And so your product is going to be that over there. And then your other product would be, so this Br is going to switch places. So all you're going to be left with now is HBr. Reaction E, so that's this one over here. Okay, so you see how we have major product and minor product. So you know when we used, when we went from this one over here earlier, we said that we originally had this, and then we reacted that with water, for example. Actually, no, sorry, we need to go all the way back to here. When we had that alkene, we had this one over here, and then all of these were hydrogens. And what we said then was that, because we needed to know where to put the hydrogen, where to put the hydrogen and where to put the bromine. And for that, we used that Markovnikov's rule, right? Where the richer get richer. But that is how the major product is formed. But sometimes in real life, that rule doesn't get followed. It's almost like most of the products, maybe 95% of them go like that, and then the other 5%, they don't obey the rule, and they go the other way around. So they actually end up having the Br attached here, and the H attached here. So that would be the minor product, and so when you form the minor alcohol, you would have the OH being formed on this first carbon instead of on the second carbon like we saw over here. So at alcohol Z, it looks like this. Now, knowing that, they said reaction E is a reaction between minor product, which is the alcohol Z, and the carboxylic acid to form an ester. Okay, so it says write down the name of this type of reaction. Well, when you're forming an ester, we can just call it esterification. Let's write that a bit better. Esterification. And then this one says, what is the name of the inorganic product that will be formed during this reaction? Well, let's have a look at that. If you take an alcohol like this, okay, I'm just going to draw it over here, with 3 carbons, okay, and that's an alcohol. Now, if you react that with a carboxylic acid, so let's say, for example, we reacted with a 2-carbon carboxylic acid. So let's say we have the HO over there, and then the double bond oxygen over there. Okay, then what happens is that this stays as it is, and this oxygen stays where it is. And so, or let's rather say, and that all stays as it is. So what you eliminate, or what you get rid of while you are reacting the alcohol and the carboxylic acid, is you've got this H2O molecule that would be released. And that is an inorganic compound. So what is the name of the inorganic compound? It's going to be water. Or let's rather say water, because they said the name. They didn't say name and formula. What is the name of the catalyst? So we typically, for this reaction, we're just going to use sulfuric acid. And then what is the IUPAC name for the functional isomer of the ester formed? Ooh, that's a sneaky one. Because, wow, okay, hello, we ain't playing, are we, whoever sat this exam? So we know that we've got this molecule, okay? And if we, okay, so in the product, we can see that there are 1, 2, 3, 4, 5, 6 carbons in the product. So it means that, and remember this one here was a 3 carbon. So it means that the carboxylic acid that they reacted this with would also have been a 3 carbon carboxylic acid, because that is the only way you can form 6 carbons. So the product would have been 3 carbons from the alcohol and 3 carbons from the carboxylic acid. So that is called, now this isn't the answer, but that would be called propyl propanoate. But now, they said, what is the name of the functional isomer of the ester? So this is the ester that was formed. This one is the ester, but they want the functional isomer. Now, remember, we've spoken about this before. In grade 12 organic chemistry, there are only 2 pairs of functional isomers. It's aldehydes going with ketones, and then carboxylic acids going with esters. So this is a 6 carbon molecule. So the functional isomer must also be a 6 carbon carboxylic acid. So what would the name of that be? Well, that would be hexanuic, because it's 6 acid. Hexanuic acid. So just to reiterate what I've just said, we know that from this reaction, this one over here, reacting with a 3 carbon carboxylic acid, produced a 6 carbon ester called propyl propanoate. However, the question said, what is the IUPAC name of the isomer of the ester that formed? So they don't want the name of the ester that formed, they want the isomer of that ester. And so we know that the only functional isomer of an ester is a carboxylic acid. So we then went and found a 6 carbon carboxylic acid, because this one also has 6 carbons, 3 here, 3 here, and so that would have to be hexanuic acid. Draw the structural formula of the functional group of a carboxylic acid. Okay, so all carboxylic acids have the same functional group, and that goes like this. What makes something a carboxylic acid? It's when it's got a double bond oxygen attached to an OH, and then you must just show that there's this part. This part here can be whatever, but we just leave it like that. I will be splitting all these questions up onto individual pages, but here they all are. Learners are asked to investigate the rate at which you have some impure calcium carbonate will react with an excess of hydrochloric acid at room temperature to produce CO2 gas. Okay, so the key things I want you to see there is that the the calcium carbonate is impure. And another thing is that the hydrochloric acid is excess. That is its concentration. And that's about it. That's important there. So what they're doing, learners are asked to investigate the rate. So they want to see how fast can this experiment take place. So what is an investigative question? So it's a bit of a difficult one, because we don't really know what they're changing. They don't really tell us. They don't tell us that they're going to change this, or, they don't tell us they're going to change the mass of this, for example. So I don't like the question. But anyways, we could say something like, how does HCl concentration affect the rate of reaction? Okay. What is a controlled variable? Controlled variable is the thing that stays constant. So they said at room temperature, so that's definitely, we're not going to change that. So we're just going to say temperature. But there's a bunch of things you could say here. On the memo, there's a few different answers. It's not just temperature. You could even say the mass of impure calcium carbonate, for example. And then what is the dependent variable? So the dependent is like the outcome. So the outcome is going to be, so learners are asked to investigate the rate at which, so I guess it could be like And so the thing we're trying to measure in this experiment is how fast can the reaction happen. So we could just say rate of reaction. This question says, with reference to the graph, how will the rate of the reaction between time 0 and 20 compared with the rate from 30 to 50? Okay, so from 0 to 20, that's here. Okay, and then from 30 to 50, well, that's here. So what we can notice is that the gradient of the line in the beginning is a little bit more steeper than the gradient at the 30 to 50. And that's normal. As a reaction proceeds, the rate of the reaction decreases. So with reference to the graph, how will the rate of the reaction compare? We can just say that the rate at 0 to 20 seconds is then 30 to 50 seconds. This question over here says, what conclusion can be drawn from the graph between 60 and 70? Okay, so 60 and 70, we can see the line has become flat. Don't call this equilibrium. It's not equilibrium. We are not in a reversible kind of system here. If we were, that would show like an arrow or something. And we would also probably, we wouldn't have just one arrow, like we say. So what we can say is that the reaction is complete. The reaction is complete. Reaction is complete. When is a reaction complete? It's when one of these reactants is finished. Which one would finish first? It would definitely be the calcium carbonate. Why? Because they said that the HCl is the excess. Excess means that there's more than you need. This one says for 5 marks, use the graph to calculate the mass of calcium carbonate that reacted. The molar volume is 24 at room temperature. Okay, guys, so this is actually a very easy question. I know it can be overwhelming, but have a look at this. From the graph, what can we measure? We can measure the volume of CO2 gas that is produced. So we can measure this one's volume. Then they've given us the molar volume. Normally it's 22.4, but at this particular room temperature, maybe we're not at, that 22.4 is only valid at STP, the 22.4 that we've heard about. You know that Vm equals to 22.4? Well, that's only valid at 0 degrees Celsius. But now we are at room temperature, so we're not going to use this one. They've given us a new Vm. So we now have V and we have Vm. So together, what can we get from that? Well, there's a formula that uses V over Vm, so we can get the moles. Once we have the moles of one substance, we can get the moles of anything else. So then we will be able to work out the moles of CaCO3, which reacted. And once we have the moles of that, we can convert it back to mass. And that's exactly what they wanted us to do. Some of you might be saying, Kev, but isn't the mass of CaCO3 0.3? No, the 0.3 is the mass of the impure calcium carbonate. Remember, one day you're sitting in your laboratory and Tuobi, your lab assistant, he walks in and he's like, hello, sir. So I've got a impure calcium carbonate. And so he gives you that impure calcium carbonate. But remember what impure means. It means that it's not pure calcium carbonate. So what we are going to calculate in 5.4 is the mass of pure calcium carbonate. It's definitely going to be a number that's less than 0.3. Okay, so let's go do that for 5 marks. So we start with N equals to V over Vm. And the volume of CO2 gas produced, we can see, if you read it off, is 25 centimeter cube. Now we need to remember that we want to work in decimeters. So we're going to say 0.025 decimeters. And now we can go use our formula. And now we're going to divide that by 24. And that'll give 1,042 times 10 to the negative 3 mole. And that is the CO2. So now we have the moles of CO2 that is produced. So now let's just make sure this reaction is balanced. I think it is because they've got a number there. So CaCa, I'm just going to quickly go through this, guys. C, oxygen, 2H, looks balanced. Yeah, we balanced. Okay, fantastic. So we now have the moles of CO2, so we can get the moles of CaCO3. We can see that they are in a 1-to-1 ratio. So CaCO3 with CO2, they are in a 1-to-1 ratio. So then, if we know that the moles of CO2 is that, then the moles of pure CaCO3, remember that everything you see in a reaction is pure. All of that is pure. So this is the pure stuff. Okay, so now we have the moles of CaCO3, so now we can go work out its mass. So we know the moles, so we can say 1.042 times 10 to the minus 3. We don't know the mass. Molar mass you get on the periodic table. Because I've done this so many times, I know that the mass of this thing is 100. The reason is that this is 40, this is 12, and then this is going to be 16 times 3, which is 48. Okay, so that's just going to be 100. And then you're going to end up multiplying these two numbers together. We end up with 0.104 grams. So now remember, oh no, that's the answer. Wait, the molar, what did they want? Use the graph to calculate the mass. Yeah, we've done it. Perfect. Okay, now calculate the percentage purity. That's an easy question, because to calculate percentage purity, all you do is you just take the pure mass divided by the impure mass, and you just multiply that by 100. So the pure mass is 0.104. The impure was the one that Turby gave you, 0.3. And then we're going to multiply that by 100. And that's about 34.67%. Okay, so 34.67%. Okay, so now this one says, the learners repeat their investigation. Yeah, of course you learners repeat it. Why can't you just go home and be satisfied? Why do you have to keep going, nerds? The learners repeat their investigation by using 0.3 grams of the same impure calcium carbonate, but instead they increase the concentration to 2 moles. Like seriously, just go home. It's Friday. Go out, call up some chicks and go on a date. Like, why are you chilling in a lab after school to change the reaction rates? Come on, man. Trying to help you, but you got to help me. You got to pull your part, you know. I don't want you to be lazy, but I also don't want you to be chilling in your laboratory on a Friday evening. Okay, so let's anyways just help these oaks out. Okay, so what they're doing is they are deciding, like, we're not satisfied with the first experiment. We want to do the experiment again. So instead of using 1 mole per decimeter hydrochloric acid, they're going to now use 2 mole per decimeter. So they're increasing the concentration of the hydrochloric acid. Okay, so how will the gradient of the graph change when the concentration... Okay, so what they're now going to do, guys, is originally, let's just say this is originally, we had a 1 mole, what am I writing? 1 mole per decimeter HCl. So that is a concentration. Concentration tells you, like, how dense is it? Like, how many particles of HCl can you see in a certain little volume? So let's say we had, like, I don't know, 5 HCl molecules, and then we had, I don't know, let's say we've got like 1, 2, 3, we've got 3 calcium carbonates. That was the original experiment. Now, these Owens who don't want to go home on a Friday afternoon, they decide, let's increase the concentration of HCl. So suddenly, there's a whole lot more HCl floating around. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But they haven't changed the amount of calcium carbonate. So this is the new. So now we have 2 mole per decimeter HCl. So it says, how will the gradient of the graph? Well, what's going to happen is that, according to the collision theory, remember what we've spoken about in the collision theory? We've said that for a reaction to take place, the particles have to collide. Let's actually just stop right there. Would you agree with me that by having more HCl particles in the system, there's going to be more collisions between HCl and calcium carbonates? There's definitely going to be more collisions. That means that the reaction rate is going to increase. So instead of having a graph that looks like this now, it's going to be steeper in the beginning, and then it's still going to flatten out to the same position. For those of you that do very well and you get like 90s or 80s and you want to know, like, Kev, why does the graph maybe not finish higher up? Well, that is because, good question if you're asking that, that is because the HCl is in excess. So that means that even if we add more of it, the reaction is still going to stop once the CaCO3 has finished. That is the limiting reactant. So if something is in excess and you add more of it, you're not going to make any more product. Your products are not going to suddenly be up here. However, you are going to make the reaction rate faster, so you're going to reach the end of the reaction much sooner. Okay, cool. Now, we've done that one for 1 mark. So I said, how will the gradient, we said it will increase. Now, this last one says, use the collision theory to explain how an increase in concentration. Okay, so remember, collision theory tells us that in order for a reaction to happen, the particles have to collide. That's pretty straightforward. They need to have enough energy, and they need to have the correct orientation. Now, by increasing the concentration, we have a system that now looks like this. That doesn't affect the energy. The particles still have the same energy, and that doesn't affect the orientation. All that it means is that there will be more collisions, which means there's a more likely chance of effective collisions, meaning the reaction rate will increase. But let's write that down for 3 marks. So what we can say is that an increase in concentration increases the number of particles per unit volume. Okay, that's step 1. Step 2, this will cause more collisions, effective collisions per unit time, therefore reaction rate increases. Potassium dichromate is formed when nitric acid is slowly added to a potassium chromate solution. The chromate ions reach equilibrium with the dichromate ions according to the following balanced ionic equation. Okay, so we know that nitric acid is HNO3, but they haven't shown the whole of HNO3. They've just shown the hydrogen ion part, because that's the part that actually reacts. So let's just read that again. Slowly added to a potassium chromate solution. Okay, so they've also left out the potassium part. They've just got the chromate. The chromate ions reach equilibrium with the dichromate ions according to the following balanced ionic equation. Okay, so they already tell us it's balanced, and we can see its equilibrium. So it says, define the term chemical equilibrium. Okay, so the way that it works in real life is, originally, you're only going to start off with these. And then as the reaction begins to take place, the forward reaction is going to progress, and the forward reaction is going to begin to slow down. As this starts being produced, the reverse reaction is going to start increasing, and eventually we reach a place where the forward reaction and the reverse reaction are taking place at the exact same time, and that is equilibrium. So chemical equilibrium is when the rate of the forward and reverse reaction are happening at the same time. However, we must remember that when equilibrium is reached, the system doesn't stop reacting. It keeps reacting forever and ever and ever. Forward reaction takes place, and then the reverse reaction takes place. So it just goes on and on and on and on and on. And so we talk about something called a dynamic equilibrium, because dynamic means that it's still happening. All right, so here we go. Chemical equilibrium is a dynamic equilibrium when the rate of the forward reaction equals to the rate of the reverse reaction. A concentrated nitric acid solution is now added to this reaction mixture. What color change will be observed? Choose from more yellow or more orange. Okay, so check this out, guys. This system was at equilibrium, and then suddenly they decide to add more nitric acid. Nitric acid is HNO3. So we must understand that that is actually, you can think of it as H plus and NO3 minus. So do we have any of these in our reaction? Look carefully, look carefully. Yes. So what this actually means is that by adding the HNO3 to this solution, what are we doing to the amount of this? We are increasing the amount of that. Now think about Le Chatelier. What will the system try to do? So because the people who added the nitric acid, they increased the amount of this, the system is going to try to make this become less again. How does it do that? By going forward or reverse? Well, it would have to go in the forward direction so that this becomes less again. And so the solution is going to end up becoming more orange. Okay, now this next question says explain that. Okay, so the first step is to say that when HNO3 is added, remember HNO3 is a strong acid, so it will ionize into H plus and NO3 minus. All right, now it says that when the temperature of, okay, so let me just make sure we've done everything. We've done that, we've done that, we've done that. Okay, so it says when the temperature of the original mixture is increased, it is observed that the color changes yellow. Is the forward reaction endothermic or exothermic? Okay. Okay, so I'm going to do 6.3.1. Okay, yeah. Okay, I'm going to quickly tell you what the answer is for this one. Let me just think about it quickly. Okay, it observed. Okay, so the forward reaction is going to be exothermic, and now I'm going to help you to understand it by explaining it in 6.3.2. All right, so let's think about this carefully, guys. So what was done? They said that the temperature is increased. Okay, so I want you to think about that. The system temperature was increased. So immediately, what is the system going to try do now? Is it going to try increase the temperature or decrease the temperature? Well, remember, the system temperature was increased, so according to Le Chatelier, the system will immediately try to do the opposite. So the system will react in such a way so as to decrease the temperature. So guys, how do you make something more cold? What makes you think of more cold? Exothermic or endothermic? Which one is cold? Endothermic. So we can say that the endothermic reaction will be favored. But Kevin, I thought you said exothermic. Guys, we're getting there. Just you'll see. Endothermic reaction will be favored. Okay, so we know that that's what the system will do. It'll go for the endothermic reaction so that it can make the temperature lower again. So we know that. Now they said that when this system reacted, the color of the mixture changes yellow. So that means that this reaction was being favored. That's why it became yellow. And so we can say that the reverse reaction was favored. How do we know the reverse reaction was favored? Because they told us that it became more yellow. So that can only happen if the reverse reaction is favored. Okay? So now, look at these two statements and make a conclusion about the forward reaction. They said is the forward reaction. So if the endothermic reaction is being favored, and we know that the reverse was favored, that means that the reverse reaction is the endothermic. That means the forward reaction must be the opposite. So forward reaction is exothermic. And now we need to tackle the big boy. Okay, 8 marks. Right, let's see. 11 moles of CrO42- and X moles of H plus are initially added together to make a 0.5 decimeter solution and allowed to react. Okay, so this is definitely a KC table kind of vibe. So let's go and draw ourselves our table. Okay, so in the table, we always want to show the reaction. Then we want to show the initial moles. Then it's the change. Then it's the moles at equilibrium. Then it is the concentration at equilibrium. All right. And we've got, so remember in the table, we only, okay, well, I guess we're going to go put everything. All right. Okay. So CrO42- H plus Cr2O72- H2O. Okay, now they tell us that initially we have 11 moles of this stuff, X moles of that, and then these we will just make them 0 because they are products. Now it says when the reaction reaches equilibrium, the solution contains this concentration of this stuff. So concentration at equilibrium over there is 9. Okay. Calculate the initial moles of H plus, so they want you to calculate X if the equilibrium constant is 0.09. So Kc is 0.09. Okay, so what we're gonna do, guys, is we're gonna start here and we can work back one step. So we know that this line is concentration, this is moles. So the relationship between them is this formula over here. So we can fill in the concentration. And then the moles, we don't know. The volume of the container is 0.5. So yeah, that 0.5 is the entire container volume. So you say 0.5. Then if you had to calculate N, you would get 4,5. So we put 4,5 over here. Now, how do you go from 0 to 4,5? Well, that means you must go up by 4.5. Now I want you to imagine that I put my hands on your shoulders right now and I say, look at me in my eyes. This row is the most important row in the entire table because it tells us what happens in the reaction itself. So as long as you have the numbers in the front, you can fill in all of the others as long as you have one of them. So we can see that the ratio, and I'm not really going to worry about liquid, I mean H2O. Why? Because it's a liquid. We don't worry about liquids and solids. We only worry about gas and aqueous. So if we now look at the ratio of this, it's 4.5, sorry, it's 1 to 2. So that means that if this one is 4.5, then this one is going to be 9. But because this one is a reactant, it becomes less. And then this one is also going to be a 9, but it's also a reactant, so it becomes less. Now we just do basic maths. 11 minus 9 is 2. This will be x minus 9. And then we can carry on. So now we can work out the concentration over here by using C equals to N over V. And so we can say the moles is 2 divided by 0,5, and that's going to give you 4. And then here you're going to get x minus 9 divided by 0,5. There we go. Done. Now we can go look at Kc. So we know that Kc is the ratio of all product concentrations over reactant concentrations. So the products are going to be only this one. Remember, we don't look at liquids and we don't look at solids. So it's going to be the concentration of Cr2O72 minus over the concentration of Cr042 minus. Now remember that these numbers in the front, they are exponents, okay? And then it's the concentration of H plus squared. Okay, and we know that the Kc value is supposed to be 0,09, or let's just say Kc for now. And so we end up getting 0,09 equals, now the concentration of Cr02 is Cr2O7 is 9, and the concentration of that one is 4 to the power of 2, and then x minus 9 over 0,5 to the power of 2. Okay. So now we eventually want to get this one, right? So what I'm going to do is there's multiple ways you could handle this. I'm going to leave this number as it is, and I'm going to leave this number where it is, and I'm going to take this and multiply it over to the other side. So we're going to end up with 0,09 x minus 9 over 0,5 squared, and then that you can just type on your calculator. It's going to become 9 over 16, and then to get rid of this, I'm going to divide it on the other side. So you're going to end up with x minus 9 over 0,5, and you don't have to do it the way I'm doing it. There are so many different ways. I'll be honest, if I wasn't teaching right now and I was actually just doing this myself, I would actually do something totally different. I'd do like a trick. So there's so many different ways of doing it. Okay, Kevin, no need to flex. It's not like you've been doing this for like your whole life. Okay, so if you type in 9 over 16 divided by 0.09, you get 25 over 4. Okay. What I'm then going to do is I'm going to square, see there's so many different ways to do this. Instead, I'm going to, you know that when you have a 2 here, that means that it's the top and the bottom squared. So I'm going to say it's going to become x minus 9 squared, and then the bottom is going to become 0,25. If you square that, it becomes 0,25, goes to 25 over 4. I'm then going to multiply this up to that side, so it ends up becoming x minus 9 squared equals to 25 over 4 times 0.25, and that gives us 25 over 16. All right, starting to look quite nice. I'm now going to take a square root on both sides. Remember that gives us a plus minus over here. One of the x answers will probably be negative, which isn't allowed. So we can end up with x minus 9 equals to plus minus. Now the square root of 25 is 5 and the square root of 16 is 4. And so we end up with x equals to 9 plus minus 5 over 4. Okay. So, oh no, it's not going to be a negative number. So for the first answer, we're going to get x as 10.25. And then for the second answer, we're going to get 7.75. And x is a mole, so we could say mole. Now we just got to think, are both valid? Okay, they can't both be valid, because if x is 7,75, if you had to put 7,75 here, then you can't change by 9, because imagine you have 7,75. If you say minus 9, then that means it's impossible in the real world, because if you only have 7.75 moles, how can it go down by 9? Then you're going to end up having negative moles. So this one is a no solution. So then the answer is 10,25 mole. A solution of carbonic acid has a pH of 4.2 and the following Ka value. This is enough to give a student a heart attack. Don't worry, guys, it's not that scary. We're gonna crush this one. A solution of sulfuric acid has the following. Guys, I'm actually cool, I promise. Like, that noise I just made now, I promise I'm not like chilling in my room now with like thousands of maths books around me and cats all around me, and I haven't cleaned up the cat urine, and I'm just like nerdy. I'm cool. I'm a wicked cool guy. Woo. Okay, ladies, take it easy. Okay, a solution of sulfuric acid has the following Ka value. Oh, okay, so the Ka value is of that, and the carbonic. Hello, I'm Afrikaans. Carbonic. Okay, the carbonic acid is that. This question says, calculate the concentration of the hydronium. Hydronium is H3O+. In the carbonic acid solution. So even though we might not know what carbonic acid, you might not know the formula, it doesn't matter for that question, because we know that pH is equal to negative log of H3O+. And so we know the pH is 4,2. And so that's equal to negative log of H3O+. And now we just have to reverse log. So remember that the 10 is, there's a base 10 there. What I like to do is put the negative on the other side. And so now it's this. And then all you do is you just say 10 to the negative 4.2 is equal to the H3O+ concentration. The way it works with logs, by the way, that 10 is called a base. The base stays the base. When you're switching from exponential to logs or logs to exponential, the base stays the base. So you see how here we had a base 10, now we still have a base 10. All you're doing is you're just switching these two things around. Okay, but whether you go log to exponential, exponential to log, the base stays the base. All right. If you didn't hear me the first time, sorry, I get a bit repetitive sometimes. Okay, so 10 to the negative 4.2 is, calculate the concentration. Okay, so that's the answer, 6,31 times 10 to the negative 5 mole per decimeter to the negative 3. As I was saying, the base stays the base. Have you guys heard that song? I think it goes, the bass and the tweeters make the speakers go to war. The mighty trumpet make the big down to the floor. Then tell me where the beat drop. Tell me where the beat drop. Beat drop. I don't know if you guys have heard that, but I have, because I'm cool. Okay, so this one over here. How will the strength... Okay, I need to focus. How will the strength of the carbonic acid compared to that of sulfuric acid if both acids have a concentration of 0,02. Okay, so how will the strength of the carbonic acid compare? Okay, so immediately I can tell you that carbonic acid is weak and sulfuric acid, what's weaker than sulfuric acid. If you didn't even know weak and strong, it doesn't matter. You can just look at the Ka value. Let's make a note. Ka value is a number that tells you, Nelly wrote tells you, tells you, Ka value. Well, it ionizes. Okay, so if the Ka value, if Ka is large, it ionizes. Well, I don't really want to write that down because you can't really say what's large and what's small. But in summary, if this one has a Ka value that's larger than this one, then it means that this one ionizes more fully or more completely than this one. So it says that how will the strength of the carbonic acid compare to that of sulfuric acid? Well, the carbonic acid will be weaker than, and the reason is that it has a lower Ka value, which means it ionizes less than the sulfuric. A solution of vinegar can be neutralized with a solution of sodium hydroxide. The reaction takes place according to the following balanced equation. Okay, so they told us that it's balanced. The sodium acetate produced, which is this one, can undergo hydrolysis. Define the term hydrolysis. So the word hydrolysis comes up in organic chemistry and in acid and base, the section acids and bases. Now this is obviously acids and bases, so we just have to do it from that perspective. So hydrolysis is that thing that happens when you take a salt. Now a salt is the product of an acid-base reaction, and then that salt reacts with water and it changes the pH. So this is not the proper definition. I will get it for you now, but in summary, a salt, which is the product of an acid-base reaction, reacts with water, and this causes the pH to change. Okay, now the proper definition. Hydrolysis is the reaction of a salt with water. So basic. Well, no, not basic, because it's, acid bases, get it? Hydrolysis is the reaction of a salt with water. Done. Okay, this question over here. Will the pH of the sodium acetate be greater than or less than 7? Good question. I'll help you with that now. Kevin, of course you will. That's kind of the point of this video. Yeah, that was a bit of a stupid statement. Okay, this whole hydrolysis thing is pretty awesome. What you do is you take the salt, and let's just write it down quickly. Now I want you to break it up into its ions. So that's going to be there. So it's going to be CH3COO minus and Na plus. What I want you to then do is have a look at this one and see, where does it come from? Did it come from this one or did it come from this one? Well, that came from that one over there. Okay, so let's just say that it came from there. And then this one over here, well, that obviously came from there. So what we now do is we ask ourselves, is the thing that it came from a strong or a weak acid or base? So this over here, you must know by definition, is a weak acid. And this over here, you must know from just by memory or definition. Sorry, I meant by memory. You need to just memorize it. This is a strong base. So hydrolysis doesn't take place with anything that comes from a strong acid or base. So this thing is not going to do anything. This thing is not going to undergo hydrolysis because it came from, there it is there, it came from a strong base. Hydrolysis is only something that happens with when something comes from a weak acid or a weak base. So this one over here is now going to react with water. So we put it in as water. And you know why it's reacting with water? Because it is not happy being like this. It wants to go back to what it was. So let's put that as the product. And now what you got to just do is think about what the other product will be. So you got to think about, look at the difference here. Can you see that the only difference is that here it doesn't have this hydrogen, and here it does. Where did it get that hydrogen from? It got it from this water molecule. So what is this water molecule going to have remaining afterwards? Well, it's only going to have an OH negative. Okay, so you need to make sure you understand this reaction. Now you got to look at this and ask yourself, what does that do? Does that make pH go up or does that make pH go down? When you look at this, do you think more of base or do you think of more of acid? Well, this thing is base. This is associated with a base. So if we are producing base in our reaction, what does that do to the pH? Well, base pHs go up larger than 7. So it says, will the pH be greater than or less than 7? It's going to be greater than. Okay, and then when you explain your answer, you actually then only going to show this reaction, and then you're just going to summarize and say that the reaction produces OH minus, which increases the pH. An unknown carbonate has a chemical formula like that. A learner is identified. A learner is asked to identify element Y. The learner adds that many grams of carbonate in a conical flask containing 25 centimeter cube of hydrochloric acid solution with a concentration of that. The balanced equation is there. The hydrochloric acid is in excess. Okay. First question. Calculate the initial mole of hydrochloric acid in the conical flask. That's easy. They gave us the volume of hydrochloric acid and the concentration of hydrochloric acid. So we can just use C equals to N over V, where the mole, we have the concentration, sorry. And the moles is what we're trying to find. And then the volume, remember that 25 centimeter cube is 0.025 decimeter cube. I divide it by 1,000. And so we end up with, okay, once the mixture has stopped fizzing, this much NaOH is added to the mixture to neutralize any remaining hydrochloric acid. Okay, let me pause right there and help you guys understand what the heck is going on. Okay, guys, so let's do this carefully. What we had originally was we had a flask. Okay, originally, let's say at point number 1. So forget about all of just up to here for now. In this first flask, the learner adds the carbonate. Okay, so we add the carbonate and we add some hydrochloric acid. But they tell us, and these two are then going to react. So in this container here, those two are going to react according to that reaction over there. However, they tell us that the hydrochloric acid is in excess. That means that there is too much. That means that when the reaction is finished, there's still going to be some hydrochloric acid left over. What we have calculated in this first question was the total amount of moles of HCl that we have in this container in the beginning. But that doesn't mean that is how many moles we used in the reaction over here, because they told us that there is excess. So we don't know how much HCl we used in this reaction. You cannot say it's this much because, like we've said, the HCl is in excess. All that this number represents is how much HCl we started with in the beginning of the question. Okay. So now what they do is they realize after this reaction has finished, which of these is no longer going to be in the container. Let's check your understanding. After this reaction has finished, which one is not going to be there anymore? Well, there will no longer be any carbonate because that is the limiting, and then there will still be a little bit of HCl left over. So going into the second part of the question now, there is still some HCl. Okay, so this is now phase 2 of the question, and that's where we start going into this one over here. So this HCl is the remaining HCl from reaction 1. Okay, but the carbonate is no longer there because the carbonate has been reacted. So what we can now do is move on to this part of the question. And we can now realize that they have now added NaOH. Now we know that NaOH and HCl are going to react. It's a typical acid-base reaction. They haven't given it to us because it's such an easy one. It's a base plus an acid giving us a salt and a water. You don't even have to balance it. It's already balanced. Yeah, it's already balanced. Okay, so check this out, guys. They gave us all the information we need for NaOH. They gave us its volume and its concentration, so we could work out the moles. Once we have the moles of this one, we can work out the moles of HCl, which would be the moles of HCl that reacted over here, which is also the moles of HCl, which is the remaining from this reaction. Okay, I hope you're understanding the bigger picture. Okay, so we're going to go work out the moles of NaOH by using this formula. And we know the concentration is 0.1. The moles we don't know. And then the volume is going to be 0.015. Remember to always convert this to decimeters by dividing by 1,000. If you had to work this out, you should get 1.5 times 10 to the negative 3. And that is the moles of sodium hydroxide in this reaction. So now we can go get the ratio of HCl to NaOH. We can see that from the balanced equation, it's 1 to 1. So if we have 1.5 times 10 to the minus 3, then this will also be 1.5 times 10 to the minus 3. So now we know how much HCl was in this reaction. So now we know that in the very, very, very beginning, we started with this amount of HCl. We know that in reaction 2, this is how much was still left over, because that is how much was able to react over here. So then how much did we actually use in this part over here? It's almost like this. One day, a mom gives her son 20 rand. Her son comes home with 3 rand. How much money did the son spend at school? Well, you just minus them. So one day, I gave you this many moles of HCl, and I know that in this reaction, all that you had left over was 1.5 times 10 to the minus 3. So how much did you use over here? Well, you just minus them. Okay, and so if you had to go and subtract those, you end up with 6 times 10 to the minus 3. So 6 times 10 to the minus 3 mole. Okay, so now we know the moles of HCl that were used in this reaction. So now we can get the moles of this carbonate. Okay, so we can see that the ratio is 2 is to 1. And so the HCl that we used there is 6 times 10 to the minus 3. So then this would be 3 times 10 to the minus 3. Now we have the moles of Y2CO3. And now we can go use N equals to M over M. So we have the moles, the mass they gave us, 0,5865. And then the molar mass from the periodic table we can just leave as M for now. Okay, so if we then had to multiply the M over to the other side, we then end up with that. And so the molar mass in the periodic table, you end up with 195.5 grams. Okay, now we know that the formula is Y2CO3, where Y is the unknown. That would be an unknown element. So we know that the mass, we can get the mass of this. So we can say 195 minus 5 minus, so 195,5 minus the mass of carbon on the periodic table minus the mass of oxygen, which is 16 times 3. And that'll give us 135.5. So that means that the Y2 must be 135.5. So then what would Y be? Well, divide by 2. So you end up with 67.75. So now we're going to go look on our periodic table for something that is similar to that in mass. And so you're not going to find something with exactly 67.75, but what we do find is zinc is pretty close. This is even closer, to be honest. But on the memo, they got 67.75, and then they just said, okay, it's zinc. So that is a bit weird. I would have expected them to design the question such that they get it exact. But anyways, they got exactly this on the memo, and then they just said that it's zinc. But as long as you understand the idea of what we did, that's fine. Okay, here we have some electrochemistry. Which electrode is the cathode? Write down only nickel or cadmium. Okay, so you can't just look at this and figure it out. You need to look at your table. Okay, so the table that I always use is table 4b. So it says which electrode is the cathode. Okay, so we go find the nickel and the nickel plus 2 on our table. There it is. Okay, and then you go find the cadmium and cadmium plus 2, which is, over there. Okay. Now remember, the way that we want it, for this reaction to be spontaneous, which it is when you have a galvanic cell like this, then you want to create a positive gradient on this table. So something like that. Okay, you don't want it to go that way. That would only be if we were using table 4a. So on table 4b, spontaneous reactions are when you can create a positive gradient. So you can also use the arrows like I've explained in previous videos. You want to choose the one that's highest up on this side. So that would be this one. And then you want to choose the one that's lowest down on this side, which would be that one. Okay, but it's the same thing. You see how it creates a positive gradient? Remember, that's a positive gradient in maths, and that's a negative gradient. Okay, so then once you've circled that, the direction of the reactions is going to go like that. So it means that nickel 2 plus is going to undergo reduction to become nickel. Remember, whenever these reactions go this way, that's reduction. And whenever they go that way, that's oxidation. So this is where reduction is going to happen. And then this is where oxidation is going to happen. Okay. So that means that it says, which electrode is the cathode? Well, we know that reduction is always where cathode is, and then oxidation is always where your anode is. So which electrode is the cathode? It's going to be the nickel. Write down the equation for the oxidation. Well, that's this one. So it's got to be written in the direction that we have it. So it starts with cadmium, then it becomes cadmium 2 plus 2 electrons. You see? So it starts with cadmium and then goes to cadmium 2 plus. So let's write that over here. Cadmium goes to cadmium 2 plus 2 electrons. Okay. How will the reading on the voltmeter be affected if the concentration of the nickel ions is increased after the cell has reached equilibrium? So we need to go, to be able to understand that kind of question, we have to go write out the balanced equation first. So we know that the oxidation reaction, we've already written that one down, goes like this. And then the reduction reaction goes like that. Then to put these two together, you want to make sure the electrons are the same, which they are, so we don't need to do anything weird. So then you're just going to put everything on the left side of the arrow together, and then everything on the right side of the arrow. And then the electrons cancel out. So this is the balanced equation taking place in this cell. Okay, so they said, how will the reading on the voltmeter be affected if the concentration of the nickel ion, so not the nickel, not this one, specifically the nickel ion. So remember, your nickel ion is this one. So think about Le Chatelier now. If you increase the concentration of this, what is the system going to try to do? The system is going to try to decrease the amount of that again, so it's going to go in the forward direction. As soon as these reactions go forward, the voltmeter reading goes up. As soon as the reactions go in reverse, the voltmeter readings go down. So how will the reading on the voltmeter be how will it be affected? It will increase. Now that whole question is for 2 marks, so we don't need to go into the whole like Le Chatelier in detail. We've already gotten 1 mark just for saying that. So your next thing is just a 1 mark. So we can just say that by increasing Ni2 plus, the, and it's the concentration, say that the forward reaction will be... Alright guys, I want to quickly give you my POV. It's a Friday night, and I am finishing this paper. It's about 8 o'clock at night. A couple of my friends asked if I'd like to go out, and I said, look, I will see, but I've got to finish this exam paper because all the students are writing on Monday. And yeah, I decided I'm not going because it's taking a lot longer than I expected. But hey, that's sometimes we have to make sacrifices in life. And yeah, I don't actually care. I love recording. So I'm in my happy place. I have a nice cup of coffee next to me. It's so nice and cozy. I have a little dog as well, Pug. But the problem is I can't have her in the room with me while I'm recording, because if you have a pug, you'll know what I'm talking about. Like it's... They just snore all the time. She doesn't even sleep in the same room with me. She sleeps in the lounge because the snoring is just intense. It's intense. Some people like it, but I can't take it, I would get annoyed. So anyways, let's do this question, guys. Consider the following standard electrochemical cell. Okay, so we've got a copper cell and a silver cell. So this is like a normal galvanic. You should understand that the one that's on the left, when they write it like this in cell notation, the one on the left is always the anode. Okay, that's just like a format that scientists around the world use. And this is always the cathode. So if we had to draw this bad boy, it would look something like this. There's your salt bridge. And then we're going to have a solution and a solution. And we're going to have copper 2 plus. And then a copper electrode. Let's make it a little bit thicker. Copper. Usually we have like a voltmeter. And then this would be a silver electrode. And then the iron silver ion as the solution. Okay, so nothing fancy, just a normal galvanic cell. That's what we have in this question. They tell us that initially each half cell contains 200 centimeter cube of electrolyte. Okay, so that's just the volume of the solution. Okay. And they say that the cell is then connected to a circuit and allowed to produce a current. So we know that electrons flow through the wire, right? When you've got this system happening here, we've got electrons that flow, and so that produces a current. And then they keep doing that until the concentration of the electrolyte in the cathode becomes 0.5. So initially, I forgot to write this down. Initially, the concentrations are 1 mole per decimeter. So that's the initial concentration, 1 mole per decimeter. And this one is also 1 mole per decimeter. Now, what we must understand, if you understand your galvanic cells fairly well, is that over here, we're going to look at the reactions now, guys. I'm going to go look at, actually, I'll go get the table now before I explain this. Let me go get, okay. And so what we must understand is that they said that the Cu2 plus is the anode reaction. So that is this one over here. So because that's the anode reaction, we must understand that anode is always oxidation. So that means that that reaction is actually going to go from right to left like that, because that's oxidation. And then the cathode reaction is the one with Ag plus and Ag, and that's going to be reduction, because reduction always happens at a cathode, and so that's going to go in that direction like that. Okay, so what I want you to understand, guys, and I'm actually going to I'm going to draw this a little bit bigger because it's really going to help with 8.2.2, but I just want us to understand everything so long. Is that, try to draw this a bit bigger. So in this liquid, we've got Cu2 plus, and then the electrode is the copper the copper metal itself, and then we've usually got some type of voltmeter, and then the electrode, and then inside we have the Ag plus liquid. Okay, so what we know, and then obviously we need a salt bridge. I was just testing to see if you're awake. So obviously what we can see, and once we finish this question, it'll make even more sense. But what we have is the copper, this copper over here, is going to eventually convert into ions. It's going to convert into ions. So what's going to happen to the amount of this? What would you say? The amount of that, this over here, the ions are going to go up, and the amount of this copper electrode is actually going to go down, because this copper is going to be converted into copper ions, just like the reaction shows us. And then on this side over here, we're going to take the Ag plus ions, which are these ones, and they are actually going to convert into Ag. So you're going to start seeing a big lump of Ag being deposited over here, and the amount of this is actually going to go down. So just to summarize, the amount of this is going to go up, and the amount of this is going to go down. So you see how we originally started with 1 mole per decimeter for each container, right? Like we said over here earlier. And then they told us over here, the cell is connected, blah, 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 blah. And until the concentration in the cathode, so this is the cathode, they said that the concentration of the electrolyte is going to go down to 0.5. So it's going to go down to 0.5, but it was originally 1. But that makes sense, because what did we just say about this electrolyte? What did we say about this Ag+? We said that it's going to decrease. So it makes sense that the concentration is going to decrease in this half cell, but in this half cell it's definitely going to increase, because we said that this is going to become more. Okay, and so first question says, write down a balanced equation for this cell reaction. All right, so all you're going to do is you're just going to go write out these two reactions, but you got to start with, for example, this one, you got to start with copper. So we start with copper, and then the reaction becomes Cu2 plus 2 electrons. Okay, so you got to write it in the direction that it's going, and then this one starts with Ag+, and then it pluses 1 electron. I actually want to put the arrows on top of each other. And then it turns into Ag. Now what they want is for us to balance this thing and turn it into a overall reaction. So the way that you do that is you're going to plus these two reactions together, but we have a bit of a problem. that problem is that here we have 2 electrons, but here we only have 1. So in order for the electrons to cancel, we need them to be the same. So what we'll do is we'll multiply this reaction by 2. So we can put a 2 there, a 2 there, and a 2 there. Now what we're going to do is we're simply going to add the 2 reactions together. So on the left, we're going to have Cu plus 2Ag pluses plus the 2 electrons. And then on the right hand side of the arrow, we're going to have Cu2 plus 2 electrons plus 2Ag. What you'll notice is that the electrons are going to cancel because they're the same on both sides, but that's what we wanted. So we can just get rid of them. And then let me just neaten everything up. And so that would be the answer for 8.2.1, this part of here. That is the balanced overall reaction. And so that also helps us to understand why the concentration of the cathode is going to go down, because what we can see is that this Ag plus is starting as a reactant and then it's converting into Ag. So like we said, the amount of Ag is going to go up and the amount of Ag plus is going to go down. And then if we look at the copper, we can see that we're starting off with copper, which is over here, and then that's going to convert into Cu2 plus. So the Cu2 plus is going to end up becoming more, and the Cu is going to end up becoming smaller. You're going to pieces are going to start breaking off as it converts into Cu2 plus. Okay, so make sure you understand what this reaction is telling you. It's telling you everything you need to know. All right, this one over here for 7 marks. It says calculate the concentration of the electrolyte in the anode half cell when the cell is disconnected. Okay, so we know that originally, in the very beginning, we started with 1 mole per decimeter. 1 mole per decimeter, and each solution was 200 centimeters cubed. Remember, they told us that over here. And it's exactly the same for this one, 200 centimeters cubed and 1 mole per decimeter. And they want to know what is the concentration of this electrolyte in the anode going to become after a bit of time. Okay, now we know that it's going to become larger than 1 because we said that the amount of this is going to go up. And we know that the amount of this is going to go down. They told us that that one actually ends up becoming 0.5 mole per decimeter. So this is the initial, and this is the final. Okay. So what we have in the very beginning is we could use this, and we could work out the moles of Cu2 plus, and then we could also use the same in this one, and we could work out the original or the initial moles of Ag+. So let's go do that first. So initial electrolyte moles. Okay, so we're going to use C equals to N over V, and we know that the concentration is 1. We can actually just do it for both of them because they both have a 200 and they both have a 1. So the number of moles we don't know, but the volume is 0.2, because remember the 200 must be converted into decimeters. So if you had to work out the number of moles, you're going to get 0.2. So therefore, the Cu2 plus is going to be 0.2 moles, and the Ag plus is going to be 0.2 moles. That is the initial moles of electrolyte before the reaction takes place. That is just in the very beginning. That is what they gave us, right? Okay. Now we're going to go look at the final electrolyte moles. But for that, we can only do this one because it's only this one that we understand the final. They told us that it's 0.5. So we could go use C equals to N over V. And we know that the new concentration is going to be 0.5. We don't know the number of moles, but the volume is still going to be 200. Remember that your liquid volume doesn't change. This liquid doesn't rise or drop. It just, it just stays as it is. So it's always going to be 200, okay? And so if you had to go work this out, you're going to end up with 0.1. So the Ag plus final is going to be 0.1 moles. Okay, you with me so far? So all that we've calculated so far is that in the beginning of the question, before any reaction took place, this is how many moles of Cu2 plus we had, and this is how many moles of Ag plus we had. Now, based on this information that they gave us, which is from here, we know that the final electrolyte moles is now 0.1, and we can see that it's dropped. And that makes sense because we said the amount of this is going to go down and the amount of this is going to go up. What I want us to now look at, if you look at these two, from that, we will be able to work out how the Ag plus changed, right? We know that it started with 0.2, now it has 0.1. So how much did the Ag plus change by? What was the change in the Ag plus? Well, you could just say 0.2 minus 0.1, and that's going to be 0.1 moles. Now, how did that change? Well, that changed because there was a chemical reaction that took place. So in that chemical reaction, we now know how much of this reacted. It's this number over here. It's 0.1 reacted. So we can now work out how much of this was produced. We can work out how much of that was produced because in that equation we have the mole ratios. So it's a very simple thing. Are you with me? So what we've worked out is that the Ag plus went down, its moles changed by 0.1. That's how many moles reacted. And from this balanced equation, that equation tells you how much or what took place in the reaction. So we can now look at the ratio of Ag plus to Cu2 plus in this equation, and we can see that the mole ratio is 2 to 1 because there's a 2 there and a 1 there. So we know that the Ag plus changed by 0.1, so then if you had to work out this, it would be 0.05. So that means that 0.05 moles of Cu2 plus was produced, because you see this is a product. So you need to be careful now. How many moles of Cu2 plus did we have in the very beginning? Well, we worked it out over here, remember? And what we've just found now is that during the reaction, while the reaction was taking place, we just produced another 0.05 Cu2 plus. So how many moles of Cu2 plus do we actually have in this container now? Well, now we're going to have the original 0.2, which we worked out over here, plus we've now produced another 0.05 from this reaction that took place, and so that's going to give us 0.25 moles. Now, super easy, we can just go calculate the new concentration in this container, because we now have the moles, which is 0.25, the volume doesn't change, that's still going to be 0.2, and that'll give us, I'm going to write it over here, 1.25 mole per decimeter. So notice that this concentration in this container did go up. Remember, it was originally 1, now it's 1.25, and that's exactly what we said, because we said that there's going to be more of that being produced, and in this container the concentration decreased. So have we answered the question? It said calculate the concentration of the electrolyte. Yes, we have. It's 1.25. Electrolysis is generally used in industry to produce chemicals through decomposition. Blah, 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 boring. The simplified diagram below represents an electrolytic cell used for concentrated sodium hydrochloride solution. Okay, so this is pretty much the chlor-alkali industry. If you haven't watched my video on that, watch it. It's like a short video where I just summarize the whole thing. Okay, so let's see. Define the term anode in terms of oxidation or reduction. Well, we know that anode is always the place. Anode is the electrode where oxidation takes place. That's whether we are looking at an electrolytic or a galvanic, it doesn't matter. Anode is the electrode where oxidation takes place, and then a cathode is where reduction takes place. Okay, that's done. This question here. Which electrode, X or Y, is connected to the positive terminal of the power source? Now, if you go watch that video that I've spoken about where I explain the chlor-alkali industry, you'll see that this is super, super easy to identify. But you know what? I'm feeling naughty. So I'm actually just going to summarize the entire thing for you guys quickly right now. But like I said, because I've already made a video on it, I'm going to go a little bit faster this time. So what we pretty much have is we have I'm just going to draw a simplified container like this, like that, and like that, like that, like that. And then we're going to have an electrode and another electrode, and then like a wall in between them, and then a power source. Right, but I'm going to let you decide whether we should put positive, negative. Now, we usually on the left-hand side of these diagrams, we pump in some sodium chloride solution, okay? Brine. It's a concentrated sodium chloride solution. We pump it in here, and we know that sodium chloride is actually broken up into Na plus and Cl minus. Okay, now we want the Cl minus to be attracted here. So what do you think we should make this, positive or negative? Well, this would have to be the positive electrode. So we make that the positive part of the battery or the power source, and then this one will be the negative. So what immediately happens when you pump this stuff in is that the Cl minus is automatically going to be attracted to this positive electrode, and this reaction at the bottom takes place. Okay, in which direction? Well, we only have Cl minus, so it's going to go like that. So over here, you're going to get this. Reaction: 2 Cl minus turning into Cl2, which is in the gas phase, plus 2 electrons. So you're immediately going to see some bubbles being bubbled off over here, and that is the Cl2 gas that is being produced. By the way, the whole process of the chlor-alkali industry is to produce Cl2, hydrogen gas, and sodium hydroxide. So we've just achieved our first goal. Now, what happens is that this Na plus is, or let me first remind you that this is now going to be the negative electrode. So that negative electrode has this ability to pull these positive Nas through to this side. This membrane over here that separates the two cells, it has this amazing ability that it only allows cations. Cations are positive charges. It allows them to move through. So those Na pluses are going to move through, and they're going to end up on this side of the system. Now, the other thing that we pump in through on this side is we pump in water, just normal water. Okay, so what we're going to have now is a whole bunch of water and Na pluses around or floating around, and they're going to actually compete at this electrode here. Now, I don't know if you've ever seen my video where we spoke about the electrolysis of aqueous solutions, and we said how Na plus and water can sometimes compete, and the Na plus is over here and then the water is over here, and we said that the water would always win because we can see that it is lower down or in the same direction as this arrow. Obviously, I'm using table 4b. So we said that the water is always the one that wins because it's the better oxidizing agent, and we can see that by the direction of the arrow. So the reaction that's going to take place on this side, or on this at this electrode, is not going to be the Na. It's actually going to be this water reaction going in that direction. So it's going to be 2H2O plus 2 electrons, giving us hydrogen gas plus 2OH minus. So there we've produced another gas, so we're going to see bubbles over here. So, and we've just produced our other products. We've already produced Cl2, and now we've just produced hydrogen. Okay, and then can you see what the other product is? It's OH minus. So we have a whole bunch of OH minuses floating around as well. Now you might be wondering, Kevin, are those OH minuses maybe going to be attracted through to this positive terminal? Now remember what we said, this diaphragm or this membrane that separates them, it only allows cations through, which are positive charges. It doesn't allow negative charges to go through. So we don't have to worry about the OH minus going through. So all that we have now is a whole bunch of OH minuses and Na pluses floating around. Well, guess what? They can combine to become NaOH, which then flows out here. And there we have produced our third product. I'm not going to speak any more about that. As I said, I have made a video on this that is in more detail, but that is the basics of the chlor-alkali industry. So let's go do that exam question now. Okay, so we've done 9.1. Now it says 9.2. Which electrode, X or Y, is connected to the positive? Well, we just learned now that we know that this is the sodium chloride, which is the Na and Cl minus. Now we wanted the Cl minus to be attracted here, remember? So that means that this one has to be positive. So it's going to be electrode X. Now what's the reason for that? We can just say that electrode X needs to be positive in order to attract the Cl minus ions. Okay, this question. Write down the name or chemical formula of gas A. Well, if you just looked at that little explanation I gave here, we knew that gas A was the Cl2 that's being given off. So it said the name or the formula, so you could say chlorine gas or just Cl2. And then it says, what is compound C? Well, remember, we said that what gets pumped in here? Water, right? Remember, we spoke about it over here. Okay, and then, oh, so that's going to be H2O. Now, write down the equation for the half reaction that takes place at the cathode. Now, we know that cathode is always the place where reduction happens. Now, remember what I explained over here. On this side, we had this reaction take place. Now, you need to know that that is a oxidation reaction. And then on this one, we had this reaction take place, and that is a reduction reaction. So that's the one we want to write down. And so from that slide on the next page where I explained all of it, it was this reaction over here. So that is a reduction reaction. So we can just write that down. 2H2O plus 2 electrons gives us H2 plus 2OH minus. Okay, just want to make sure, write down the equation. That's all we need to do. Now it says for this question, refer to the relative strength of oxidizing agents to explain the answer. Write down the equation. Oh, okay, so they pretty much want to know, like, they're pretty much getting at, like, why is Na plus not reacting and why is 2H2O react? And so what we have discovered in previous videos, as well as I explained it briefly again on the slide that I showed a few minutes ago, is that we've looked at this in a video in the past with the electrolysis of aqueous solutions, and we said that often when water and sodium ion are competing, these two, we look at the arrow and we can see that water is, if you look at the direction of the arrow, water is a increasing oxidizing agent, right? I know that that's his ability, but it's the same as increasing oxidizing agent. So water is the stronger oxidizing agent. So refer to the relative strength to explain your answer. So we can just say that H2O is a stronger oxidizing agent than Na plus. And that's not going to get us 3 marks. So you should say water is a stronger oxidizing agent than Na plus, and then add to that, and is therefore reduced to, and we can see that it's going to get reduced to hydrogen and OH minus.